All right, we're going to go ahead and get started. Hi, everybody. My name is Bianca Martinez-Penn. I am the communication staffer here at the Chesapeake Bay Program, and we are excited for y'all to join us today for this webinar in collaboration with our land use team. This is Mapping Change, New Data for Land Use and Hydrography in the Chesapeake Bay region. So without further ado, I'm going to go ahead and present our speakers, introduce our speakers today. First, we have Dr. Matt Baker with the University of Maryland in Baltimore County. He joined the Department of Geography and Environmental Systems at the University of Maryland, Baltimore County in 2008, but he has been hugging trees as long as he can remember. Dr. Baker's expertise includes basic and applied research in applied ecology, quantitative analysis, hydrology, as well as geographic information systems and remote sensing. Next, we have Sarah McDonald. She is a geographer with the U.S. Geological Survey at the Chesapeake Bay Program Office. She's also a member of the Chesapeake Bay Program's Geographic Information Systems and Land Data teams. And finally, we have Alicia Sabatino. Alicia is a web GIS developer and cartographer for the Chesapeake Conservancy's Conservation Innovation Center, or the CIC. She works across CIC projects to improve the usability of GIS data for Chesapeake Conservancy clients, partners, and the general public by producing interactive web applications and static geospatial visualizations. So thank you to all of our speakers who will be presenting today. And we'll go ahead and get started with Dr. Baker. So I'm going to go ahead and stop sharing my screen, and Matt, you can go ahead and start sharing yours and we'll get started.
Okay, everyone. Hello, I'm Matt Baker from UMBC, and today I'm going to be talking about our hydrographic data release, which was produced by myself, David Saavedra from the Chesapeake Conservancy, Dr. Shuazu Kang from my lab, and Labib Ahmed from the Bay Program's USGS Land Data Science team. Like you see on the screen in front of you, we've had high-resolution terrain models for some time. So today what we hope to show is how stream maps produced from such surfaces offer something new and vital to the Bay Program's efforts. So why are we making more detailed stream maps? First, they are a record of current status that is essential for documenting future changes to the landscape and how water moves across it. Second, they provide a more accurate accounting of stream miles, allowing us to understand hydraulic geometry, or the way that different landscapes generate rivers and how those rivers increase in size, allowing us to better understand water supply, pollutant transport, and aquatic habitat across the Bay watershed. In addition, maps help us understand how activities on the land are related to streams, whether those streams are adequately protected, and where restoration is likely to be most effective. In developing such products, it's really important to have an objective and uniform tool across broad landscapes for this type of investigation. What we're going to be talking about is a really different approach than most folks are used to. I would say that anyone with a passing knowledge of geographic information systems will be familiar with the canned hydrologic tools that are embedded in that software. Most of those were developed more than 40 years ago, and they were developed for very coarse digital data sets. And the challenge was using those conventional tools over large areas with detailed terrain surfaces is that they involve several critical steps that have thus far eluded easy automation, and in many cases involve manual interpretation and in some cases subjective interpretation. And they involve how the DEM, or the digital elevation model, is corrected to allow for hydrologic flow, and then a critical drainage area threshold that is used to denote the location of a mapped stream. And in particular, we were interested in mapping streams where they are, because such thresholds change over very local landscapes. So our approach used a relatively new interpretation of how streams should be mapped. And it started with removing relatively minor errors in the topography that could lead to major differences in the way we interpret how water moves across it. We focused explicitly on feature extraction, that is, identifying things that are likely to be stream channels, and then tracing connections between those features across the landscape to develop line work. So those two steps are really key in our process, and that's what I'm going to highlight today in talking about this data release. In our feature extraction, we used a technique called geomorphon mapping. Geomorphons are a form of land classification or terrain classification that uses computer vision to interpret the nature of a landform from the surrounding terrain. So in this map, it shows a hillshade of a local landscape with several different terrain features mapped and numbered for your reference. And what geomorphons do is they interpret the terrain around each of these features and classify them into a color-coded map. And the key for this is in the bottom right-hand corner. You can see the cool colors represent low-lying features like river valleys and depressions, and the warm colors are hills and ridges. And so we were interested in using this form of computer vision to identify stream channels. Our approach is modular and parallelized, so it can be run on supercomputers in relatively quick fashion, and we can take it apart and work on and improve different components at different times. We start with the terrain surface, the LiDAR elevation surface, like you see here, and then we map broad-scale landform features like river valleys. And here you see that map. This is the broad-scale geomorphons, and they're mapped at a 10-meter resolution. This map is part of our data release, so there's a 10-meter geomorphon map in our data release, just like the one you see here. That becomes an important component for constraining our interpretation of fine-scale features. Here is a fine-scale geomorphon map made to detect channels or channel-like features. This is also part of our data release, a 1-meter channel scale map of geomorphons. What we do in our mapping approach is combine these two, first by taking the broad scale map and identifying river valleys. So we use the valley network to constrain our interpretation of the fine scale features and extract them using the valley network. Then these extracted features become the breadcrumbs that we use to develop our stream map. And we call this a channel skeleton. And note that rather than a simple one-dimensional line, these are actually two-dimensional features within area. And these polygons then are also part of our data release, a stream polygon map. So all of these are available for all portions of the Chesapeake Bay watershed. And then what we do is we use, and that classification is developed using a machine learning technique. And then we connect the features and develop attributes about them, their characteristics, which I'll describe later. And then we connect them in a linear network and derive further attributes from that network. This line work is also part of our data release. It's the blue line network that you can download as a polygon. So we talked about feature extraction, and then what I would like to talk a little bit more is some of the advantages of doing this. The first is that we are doing something called direct detection. We are detecting features directly from the LiDAR. They're not based on any subjective or uniform threshold determination, and that means it's inherently flexible across different landscapes and different geographies. Because our stream maps are derived directly from the digital elevation surface, they're precisely aligned with the channel dimensions, and they also are aligned with imagery, which means they align well with the land cover data, which is developed from similar imagery. So we have much more detailed estimates of where channels are, In the map I just highlighted here, you can see an agricultural landscape with the high resolution 1 to 24,000 national hydrography data set in red, and the much more precise delineation of the channel generated with our stream polygons. When we try to connect these features, there are often gaps in the features that are created by the LiDAR surface, where streams go underneath roads, in culverts, or other features that obstruct view of the channel. And so our algorithm is connecting these features across the terrain without the need for pre-existing hydrologic correcting of the terrain surface. So we expect discontinuities, and then what we do is connect those features to generate a linear network. For every feature, every polygon, and every line, each pixel has its own geomorphon attributes, and that includes the orientation, the shape, and the extent, and that can be used to assess whether it's a consistent feature in the terrain. Those characteristics allow us to develop spatially explicit layers of channel width and estimates of bank height that are produced automatically, and each feature in a contiguous group of pixels can be analyzed as a stream polygon and allow us to separate open channel features from places where we're connecting features with the linear network. In the examples I'm showing here, we have a measure of bank height calculated for every pixel in stream polygons, and then channel widths in the bottom example that are measured within those polygons as well. These become attributes that we can summarize across the linear network, and that's part of the attribute table in the data release. So these data products are produced in a fully automated fashion at the scale of the 53 HUC-8s within the Chesapeake Bay Watershed. All processing is done at the resolution of HUC-10s or 12s. The inputs are the LiDAR digital elevation surface and the high-resolution land cover map. We denoise those LiDAR surfaces once. It usually takes about 1 to 8 hours for every HUC-8. And then we perform the channel extraction that usually takes between 2 to 6 hours per HUC-8. It is repeatable and updatable, and it takes us about 20 days to do the entire Chesapeake Bay watershed, depending on computer traffic. Two other parts of the data release include automated delineation and classification of agricultural ditches, as well as roadside ditches, also delineated in the process of making stream maps. So those are highlighted here in two examples, and those are additional ancillary products in the data release. In some cases, the ditches are part of the stream network. In other places, they are classified and distinct and left out of the blue line map. And the features that are included in both maps are places where we think the feature is part of the stream network. When we develop this linear network, we can calculate attributes that are based on that network, including stream order, as well as stream magnitude and the downstream link number, which tells you how large a stream each tributary flows into. And other attributes include the length of each line, the elevation drop across that line for gradient calculations, the distribution of channel width, and the distribution of bank heights in each reach, as well as upstream and downstream distances to the end of the network within each HUC. Finally, we calculate the proportion of connectors along each line, so it's possible to understand how much of the line is passing under a bridge or under culverts, over open water, or under the landscape surface. This map produces many more lines than currently exist in the high-resolution NHD. So in this table here, what I'm showing you are 3 8-digit HUCs from the Appalachian Mountains, the Piedmont, and the outer coastal plain. And what we're showing you is the overall area of these HUCs, the drainage density, which is the length of line per unit area for the two stream maps, the old and the new, and you can see that in each case we are more than doubling the drainage density, the apparent drainage density in the map using the hyper-resolution product, and that the rank order of the drainage density changes when we do this. And that is important understanding the way that different landscapes are connected to their stream networks and the Chesapeake Bay. Accuracy assessment in this kind of mapping is not straightforward. We have assessed 7 Huck 8s. When we performed that accuracy assessment, we focused on our effort on the low order or headwater streams without substantial overlap with the high resolution NHD. And in that accuracy assessment, we assessed 7,000 reaches stratified by order. The results are sort of up in these tables here, and what you can see is that the overlap, when the overlap is high with an NHD line, there is a high level of agreement in the headwater streams where there's very little overlap with NHD lines. Our accuracy increases rapidly with size, and the greatest error is associated with headwater channels. We assessed errors of omission, missing channels. Those were relatively rare. Commission, where our process produced a blue line that shouldn't be there. And then tracing errors, where there was some kind of problem connecting features or streamlines in our map. Partial accuracy was common, so most of our results are based on the length of the line that is accurate versus inaccurate. And this varied with physiography and land use. Just to give you a sense of how complicated this can be, here's one of my favorite examples that produced some errors. So this is a highway cloverleaf where any human modification of terrain, especially if it routes the stream underneath that terrain, can be complicated for an automated interpreter, and this was no exception. In general, the flow direction and connection is correct, but exactly how it got there doesn't always agree with the way I would do it if I was manually doing it. And this is an area for some improvement in our technique. Sometimes there's multiple layers and histories of drainage modification in a particular landscape. And what you see from doing a lot of assessment in this terrain is that humans have really changed the way that water flows in a lot of cases. And sometimes that's difficult to anticipate with an automated approach. Nevertheless, we're getting better at this and developing more sophisticated automated interpretations, and we hope to improve even more in the future. So to summarize, this new data release is coming out this week or next. We're very excited about it. We think we've produced new applications for enriching hydrographic data models and developing rapid mapping approaches over very broad landscapes. These high-resolution data provide an opportunity to rethink how we approach mapping in the first place, what features we map, which attributes are important to consider, and even though the terrain mapping approaches cannot map what it cannot see, our automated inference is improving. And we hope that this technique highlights new concepts, challenges, and potential for improvement in conservation and management. Thanks very much, and I'll stop there.
Thank you, Matt. Next, we are going to have Sarah McDonald.
Hi, thanks, Bianca. So my name is Sarah McDonald. I am a geographer with the U.S. Geological Survey here at the Chesapeake Bay Program. I'm here to talk about land use, land cover in the Chesapeake Bay Watershed. This project was a collaboration of the Bay Program, USGS, the Chesapeake Conservancy, Conservation Innovation Center, and the University of Vermont Spatial Analysis Lab. So to start, let's talk about a brief history of the project. So the first time this data were released were 2017. That product mapped the 2013 or 2014 land use conditions depending on the jurisdiction. That product was 16 classes, and that was the first 1-meter resolution land use land cover product in the region. In 2022, we released our second mapping effort, or second iteration of this data, which added the 2017-18 time period. It increased our classification from 16 to 54. And this was the first time we mapped a 1-meter resolution land use land cover change product. Today, we are releasing the third attempt at this, and this is we added the 2021 and 2022 time period to this. Our classification went up to 56 classes, and we now have 3 dates of 1-meter resolution land use land cover and 3 land use land cover change products. In 2028, 2029, we anticipate releasing the 4th iteration of this data, which will add the 2025 or 2026 timeframe. And that will be the first time we'll be using artificial intelligence to map land cover and land cover change in the watershed. What I want to highlight about this project is it is a monitoring program. So each time we map a new date, whatever rules and classification schemas we update, we remap all dates in the time series to ensure that we're consistently classifying change over time. Some high-level specs about the data. Our mapped extent, we cover 205 counties intersecting or adjacent to the Chesapeake Bay Watershed, which is 99,000 square miles. Again, this is 1-meter resolution cells, so very fine scale. We have 3 distinct dates for our temporal resolution, and for this release, our categorical resolution, we have 56 distinct land use land cover classes. So why are we doing this? Initially, the first time in 2017, the reason these maps were produced were to assess the sources of pollution to the bay, where cropland is our highest pollution and impervious surfaces are high pollution, and forest and wetlands are our lowest polluters. But since we've released this data and we've continued to improve it over time, the Chesapeake Bay Program has used it for many other projects, including reporting impervious cover, farmland and forest land conversion, wetland conversion, and riparian dynamics. So to go over some definitions, what is land cover? Land cover is the physical characteristics of the land surface. So these are things you can see from the sky, things like tree cover, impervious surfaces, herbaceous lands, etc. This product is produced by the University of Vermont Spatial Analysis Lab. This is largely driven by remotely sensed products. The main 2 inputs to these models are light detection and ranging, or LiDAR, which is used to estimate the height of features on the ground. And then the National Agricultural Imagery Program, or NAEP, is photo imagery. It's aerial photos taken from planes, and those are the main 2 inputs to producing these models. Derivatives of these products are created, including some spectral indices such as the Normalized Difference Vegetation Index and the Normalized Digital Surface Model, or NDSM. These inputs are put into a rule-based object-oriented image classification using eCognition software that produces some vector objects that they classify as a land cover class. And from there, they have a team of students apply manual corrections to the data to increase the accuracy that much more. And once they get through that process, they produce this final land cover product that you can see on the right. They produce 12 classes, including emergent wetlands, which are not going to be part of the larger release as they'll be nested into another land use. So this gives us 12 classes of land cover at 1-meter resolution. That information is then shared with USGS and the Chesapeake Conservancy's Conservation Innovation Center to translate the information to land use. Land use is how humans use the land, so residential areas, agricultural areas, parks, etc. And the main input of that is land cover. Land cover and then parcel data, which we use to assess the management boundaries of a given area. So we use that to determine kind of the ends of fields and things of that nature. But in addition to that, the translation to land use is largely driven by a plethora of ancillary data sets. Over 25 ancillary data sets were used. A couple examples here are timber harvest polygons, which All the jurisdictions in the watershed provided spatial data for us to incorporate this classification into the land use land cover. We're using other remotely sensed products derived from Landsat and Sentinel using the cropland data layer or CDL to classify agricultural classes and many others. We take all of this information and we put them into a rule-based open source Python model, thousands of lines of code that was developed by the Chesapeake Conservancy and USGS. And we use that to create a series of overlays telling us what the land use could be. And sometimes these overlays overlap each other. So then we have a separate process that then integrates all of these into producing a final land use classification in raster format. We have 28 distinct land use classes that you can see there on the right. So then we have land use land cover, or LULC. That's the combination of these two features, right? So it's describing both the physical surface and how humans use the land. So when you combine our 28 unique land uses and our 11 unique land covers, we get 56 land use land cover classes. So for example, natural succession land use and the shrubland land cover class combine to make a single natural succession shrubland class. And when you do that for the full schema, you get something like this, where you can see this is our full list of 56 classes listed here in black. You can see things like suspended succession, for example, towards the bottom left. That's our land use. You see it repeated multiple times because we have 3 different land covers that are also combined with that land use. Now, given the 56 classes can be very difficult to work with, what it does allow us to do is aggregate this information in several different ways. These are the 4 out-of-the-box aggregations that we provide in this data release. So we have the land cover aggregation, the 11 classes there on the left, our 28 land use classes. Did I get kicked out?
So try resharing. It looks like you're sharing some.
Can you see it? There we go. Sorry about that. And then finally, we have our macro classification schema there on the right. That's our highest level classification schema. It's 4 classes. And it simply represents developed areas, agricultural areas, natural areas, and water. If we look at the findings from this latest round of mapping for the 2021-2022 time period, if we look at the developed area, that makes up 13% of the entire Chesapeake Bay watershed land area at about 5.2 million acres. Of that developed area, about 40% of it is impervious surfaces. So things such as roads, structures, parking lots, solar panels, mining operations, things like that. And the remaining area of that 60%, is pervious land. So things like turf grass, tree canopy over turf grass, transmission line rights of ways, road rights of ways, landfills, and so on. Secondly, we have agricultural lands. That accounts for 19% of the watershed land area at about 7.8 million acres. And what we're seeing in the data is we're seeing a pretty even split, 50-50, between cropland and pasture and hay. And then finally, our largest makeup of the watershed is natural lands at 68% of the watershed land area, which is over 27 million acres of land. And if we look at that, the breakdown of that is about 85% forests, about 9% successional lands, 4% forested wetlands, and about 2% non-forested wetlands. Then we can also look at our trends, our change over time, between our first time period of 2013-14 and our latest time period of 21-22. In terms of acreage, the largest change in the watershed is timber harvesting. Between those 2 time periods, we see about 585,000 acres of forest transitioning to a successional state and about 150,000 acres of successional lands coming back to forest. Some of the tables we provide show the net change of any of the given classes. And if you sort that information and look at the highest amount of forest loss, you'll see that Buckingham, Virginia is the highest. But by just looking at the net change, you're kind of lacking that context of the nature of the change. So in addition to the net change, we provide something called change matrices, which allows you to look at the specific transitions of land use change over time, which you can see in the bottom left here. Each row represents the early date, in this case 2014, and each column represents the latest date, in this case 2021. So if you look at the green cell that says 39,000 acres, that's telling you that in this county, over 39,000 acres of forest transitioned to succession, and about 14,000 acres of succession came back to forest. That's different than the net change there at the bottom of 26,000. So what this is telling you is, though, even though that has the largest county with the most amount of forest decrease net overall, what's actually happening is that's mostly rotational harvest that we don't expect to be permanent. Our second largest acreage change in the watershed is to development, where about 105,000 acres of land converted to impervious surfaces. An example of this is if we look at Crozet, Virginia, it's a town that has the greatest decrease in tree canopy per acre. And if you just look at that, you might get a little bit worried, but what you're lacking is the context. So what the maps show you is what happened, where it happened, and how much. But it doesn't answer questions like, why did this change occur? What are the impacts of this change, and what are the drivers? In this example, Crozet actually are implementing well-planned development that were developed a decade or so ago, aiming to develop closer to the city center to prevent sprawl. If we look at our accuracies of the data, the Chesapeake Conservancy and University of Vermont produced an accuracy assessment where if we look at the static accuracy or where things didn't change, so these are just the areas where things stayed the same, they sampled 7,000 points across the entire mapped region. The things that don't change make up about 96% of the entire region that we map. So it's the vast majority, right, of land. And overall, we're seeing a 95% accuracy of that. And if you break it down by specific land cover type, I've aggregated them a bit here, but you can see the producers and users accuracies are quite high. The producers and users accuracies represent how likely a mapped feature is to be the thing that's actually on the ground, and how likely the thing on the ground is to be mapped as such. So we can see tree canopy, for example, is at 97% and 95% accuracy. But the bulk of this effort was actually to assess the accuracy of change. So as I said earlier, this is a monitoring program. So in order to accurately monitor the landscape, it's those areas of change that you really need to get right. So they sampled over 23,000 points of mapped land cover change, which is only 4% of the entire mapped region. And overall, what we saw is an 86% accuracy in being able to distinguish between something as change or not change. For the 96% accuracy for producers, that's telling us that we have about 96% of actual change is captured in our data, and we have 77% kind of confidence in what our change, that the mapped change is in fact change. I just wanted to take a second to highlight a couple of use cases of this data. So a couple of years ago, the Chesapeake Conservancy, University of Vermont, and a few other collaborators produced this technical study on changes in forest cover and tree canopy in Maryland. And this technical study was actually used to support the reauthorization of the Forest Conservation Act in Maryland, which is a pretty big deal. We have collaborators at the U.S. Forest Service as well that have used this data to produce these tree cover status and change fact sheets by county. So all counties that we map, they give these specific breakdowns of the tree canopy in their jurisdiction, how things are changing, and what are the benefits of tree cover in that county. And this is actually a project that is being updated now with the new data by both the county scales and finer municipal jurisdictional levels. So keep your eye out for those, that data. But both of those examples are using the previous version of the data. So I wanted to also take a minute and highlight some of the differences between the previous iteration of the data and the newest version. One of the bigger changes is that we addressed confusion of pasture and hay with successional lands. This was largely seen in Virginia, I believe, where we would have rotational timber harvests that were being misclassified as pasture and hay, which are corrected in the new data. We made some changes to our tree canopy classification, and the effects of those changes is you'll see less tree canopy over turf grass overall. You'll see more urban forests, and you'll see more forest in rural areas as well. We refined our turf grass mapping, particularly in very large parcels, so we've reduced that footprint overall. And finally, we addressed a missing solar field panel arrays class that was intended to be in the last iteration. There was an error in the model that's been corrected, and there is now a distinct solar field panel arrays class in the data. So what data is available for download? There are kind of 4 distinct areas of data that you can see on the science-based page. The first is the land use land cover raster data. Underneath that heading, it is organized by jurisdiction and then county. You're able to download the county scale cloud optimized geotiffs or COGS for the 3 dates for that jurisdiction. In addition to that, you are able to download state scale data that's in the format of a virtual raster tile or VRT. It functionally works the same as a geotiff, but without having to actually mosaic all of that information together. As I mentioned earlier, with the 4 aggregation schemas, we provide visualization layers for both ArcGIS using layer X files and QGIS QMLs for the 4 aggregation schemas, so that includes land cover. And then finally, we include a crosswalk table in the form of a CSV that crosswalks each of the unique 56 raster values to each of those aggregated schemas. Very similarly, we have the same setup for our land use land cover change rasters, again, where we have our county scale geotiffs, our state scale VRTs, our visualization layers, and our crosswalk table. The main difference with our visualization layers there is that in addition to the 4 schemas, we have different layer files to where you can visualize either the beginning or the end of a given change period. That example change matrix, we provide those for all jurisdictions in the form of Excel workbooks. So these tabular matrices are available by county, by state, the full mapped region, and the Chesapeake Bay watershed portion of each of those for all 3 change periods. And then finally, we have our region, state, and county summary tables. So these are Excel workbooks. They provide the acres of land use land cover for the 3 map dates by county, state, and the Chesapeake Bay watershed portion of both. And then similarly, we have the net change acres of land use land cover for the 3 mapped change periods, again, by county, state, and the Chesapeake Bay watershed portion of both. Now, that was a lot of information. You may be thinking, I'm not going to remember that, but there's a good place for you to start. We've developed a user guide. Folks on my team, Jackie Pickford, have put a lot of effort into making this as accessible as possible. So if you go to the science-based page, our main page available, this is where you'll be directed by clicking our DOI. If you scroll down, you'll see a section titled Attached Files. And under that attached files, you'll see something called the LULC User Guide. If you open that user guide, it provides very detailed information about the structure of the data release, which can help you navigate the science-based page. It provides a log of the update since our last release. It provides tips on how to use those provided visualization layer files. It provides definitions of each of the classes for all of the aggregated schemas and our detailed 56 class schema. It provides an example of how to read the change matrices and provides citations and a list of all of the ancillary data used to produce both the land cover and the land use. To about wrap up here, here's just our citations for the data and the user guide. Same DOI, but slightly different author list for the both. And to wrap up, here's some final thoughts from our team working on this data for the last several years, as we've kind of found that the high resolution land cover, land use, and hydrography data representing every square meter of the Chesapeake Bay watershed are foundational as they inform most of our Chesapeake Bay program outcomes, which is managed by all of the goal implementation teams or GITs here at the program. It's authoritative because it provides a fully transparent, accurate, and verifiable representation of the landscape conditions and change over time. And it's transformative because it affects the ways that we and our partners understand, interpret, and manage the landscape and make local level decisions. And with that, I will pass it to Alicia. Thank you.
All right, so I'm going to be doing a quick walkthrough and demonstration of the application we put together to view all this different data. We wanted to make an app that had all of this different data in one place. So the different pages include the land use land cover viewer, the change viewer, and the hydrography viewer. And this is all contained within one app, so you can really display all these different data sets together and compare them. And they all also allow an easy download of the data. There's also a use case submission page, which we really encourage people to start using so we can really collect all these different uses that people are using with this data. So just as a brief introduction, the land use land cover viewer itself has the download links for all the different data sets that Sarah described for each of the counties and the states for the counties in pop-ups. We include the aerial imagery and the hydrography data, as well as the land use land cover data for all 3 time periods for the current production edition. The Hyper-Resolution Hydrography Viewer has the streamlined data that Matt Baker talked about earlier, as well as download links for the HUC-8s in the pop-ups. It also includes the agricultural ditches and the roadside ditches that were described, and you can visualize the aerial imagery as well as the land use land cover data in the hydrography app. The base map is the hillshade layer, so you can see the hillshades along with the streamlined data. And then we have a change viewer as well, which has 2 panels. On the left, you'll have the aerial imagery for the first time period. And then on the right panel, you'll have the change data as well as the aerial imagery for the second time period. So I'm going to do a quick walkthrough of these different parts of the app. So here you can see the land use land cover viewer. You can change the transparency of the land use land cover data and visualize the streamlines as well. You can look at the different time periods. And then you would just click whatever county you would like to download the data for, and you'll have these pop-up links for the different matrices, the summary tables, and the different rasters. And so if you click that, that'll just take you to the county download page. The hydrography viewer has all of the streamlined data, and you can visualize this whole data set pretty quickly. If you zoom in and you want to click on a streamline and get some information, you can also see a pop-up with some of these attributes that were calculated for the streamline. And then you would just make sure you have the HUC-8 with URLs for data download layer turned on. and then you can click that and download for that HUC. This is the change viewer. And as we talked about before, you have the two panels. So the one on the left has this imagery, and then the one on the right has the time period, the second time period's imagery, as well as the change data. And you can use this top bar to change between the different views. So if I wanted to look at 2013 to 2017, I'll click this one. And I can see the 2013 imagery here, the 2017 imagery here, and the change data. So we can take a look at, you see this part was going under development, and that's captured in the land use land cover data. And if we want to turn it off, we can see it's reflected in the imagery as well. So you can use this to change between the different time periods, and your map should pan around with wherever you're going. And you can see all the change from 2013 to 2021 and just change the different time periods. And then this tab here, you can use to share your use cases. I don't want to take too long because I know we have questions. So that's the main overview of the app. I can stop sharing my screen here.
Awesome. Thank you so much, Alicia, and thank you so much to all of our speakers. We do have a little bit of time left for questions now, so just as a reminder, you can go ahead and use that Q&A box down at the bottom, or you can raise your hand and we'll bring you off of mute. Just as we do already have quite a few questions in the chat, we will say that if we do not get to your questions during the webinar, we will follow up with you via email. So we will make sure to get your questions answered, regardless if we have time for them right now. And again, we will be sending out all of the slides and resources that were mentioned today by the speakers in a follow-up email.
Well, Bianca, I can go ahead and start facilitating the Q&A portion. Thank you, everybody. Great presentations. So I'm going to answer or ask these questions in the order that they appeared. First question is from Richard Hall, and the question is, to what degree does this mapping identify streams that don't show up in USGS quad maps? And Matt, I believe you might have an answer for us.
I do. That's a good question. It varies a little bit. So the USGS quad maps, first of all, are the same blue lines that are in the 1 to 24,000 high-resolution national hydrography dataset. So we're talking about the same set of line work here. One is digital and one is maybe on paper maps or a scanned version of paper maps. So that when I show you those lines, those are the same lines you would see on a quad sheet. I can share some visuals of that to help everyone understand that. Here is an example of what that looks like. Oops. The red line is the
Matt, you might have to take over sharing again from me. Are you sharing something on the presentation or?
I'm sharing something right now. Can you not see it?
Okay, and everyone else is seeing that?
Are you seeing it, Sarah, since I can see your face? Sarah, hello? Okay.
Sorry, yeah, we can see it.
Okay, sorry, go ahead, Matt.
So this gives you an idea, Richard, about the nature of the streamlines. There are probably a couple things to note. One is that some of the extensions that we're seeing in our Hyper-Res map are headwater lines that go further into the landscape than the NHD or the TopoQuad maps do. But some of the extra line work is just from adding new streams, and they can come as tributaries or streamlines, and they can come as tributaries, but they can also come as other kinds of features like secondary channels in larger rivers or floodplain channels and ditches that might be included in our network that are not included in the USGS maps. Here's a couple of other examples of this is showing sort of like the culverts and drainages where we're going from particular channel locations across roads, and the classification of connectors versus open water features. This is the other kind of example that I think is useful. This is an overhead aerial imagery of the location where the first study on riparian buffers was done by Peter and John and Carell in 1984 at the Smithsonian Institution's Environmental Research Center in Edgewater, Maryland. And this study was really important for driving our understanding of riparian buffers, but the stream to which that riparian buffer was associated was not on any map. And so it is now on one of our maps. And this is another location near the Rocky Gorge Reservoir, which was the subject of a lawsuit where a land developer was trying to develop an area over here, and this was a tributary to a drinking water supply. So using higher resolution maps made the explicit connection of that landscape to the drinking water supply much more apparent. Okay, that's the answer, I think, to the question that was asked.
All right, thank you, Matt. The next question is, what algorithm is used to connect the hydrological connected features?
Well, for that, we actually use three because there's three kinds of connectors. The first one may be easiest to understand, and that's when we're connecting over open water, like reservoirs. In that case, what we're trying to do is route water through the center of the water feature to the downstream outlet. And there we use the open water extent mapped by the high resolution land cover primarily to delineate that water feature, and then we try to stay in the middle of that feature and then get to the outlet. So the second algorithm is how we connect features like over culverts or just over places where the stream channel disappears, like in karst topography. And in those cases, we use a combination of a cost distance surface. So the cost in this case is distance, so the closest feature, and also the topography. So the idea is to go downhill to the closest nearby feature, and that is what is used to connect the stream features. And then the third way that we connect features is in complex terrain, where like in urban areas or where there's a lot of modification of topography. And that's probably more complicated for me to explain, but basically we try to find the upstream feature that has the lowest elevation point and move from that to the downstream feature that is the most likely receptor of that flow. And there are a couple of attributes that we use to determine that. So in a lot of these cases, it's important to have attributes of the features to make that determination. Hopefully that's a sufficient answer to your question. By far, the most common way that we connect features is, and do that successfully, is with the second one.
Okay, the next question is DEM the only data input? What's the resolution of DEM and how you train your ML/DL model?
All good questions. We use a 1 meter LiDAR digital elevation surface, which is produced by the USGS, and we, rather than using the raw point clouds, we intentionally use the USGS and county level LiDAR products in the Chesapeake Bay Watershed because those are publicly available. We do smooth them, we denoise them using a form of mesh denoising to remove anomalies and to preserve signal in the terrain data. And then we incorporate that information and combine it with information from the high resolution land cover map. So those are the two primary inputs. I suppose you could say that another input that we use are the HUC boundaries, the HUC 8 and HUC 12 boundaries that we use to clip DEMs and land cover maps to perform the mapping process. Those, because they're mapped at a different resolution, do not always agree with the LiDAR or the land cover. And so we have to go through a lot of processes after the fact to correct the connectivity of our lines across HUC boundaries because the coarser watershed boundaries don't agree with the LiDAR. But those are the inputs. Hopefully that answers your question.
Matt, a follow-up to the algorithm question. It would be helpful to know the three methods, or it's helpful to know three methods, but how, all right, that just disappeared. Let me get it again. How do you identify the gaps and determine what is worth connecting versus what isn't worth connecting?
That question, I think, is in part related to the other part of the question that I failed to answer, which is the AI ML component. So we map a lot of features with the geomorphon tool, and part of the decision process is how do we get from all the features we map to the channel skeleton, which are the subset of features that we want to connect. And that is where we use training data, which we developed manually at the beginning of this process by mapping a large number of features and classifying them and interpreting them manually. And then we use that training data to drive a random forest model to select which features we think are more likely to be streams, or the algorithm thinks are more likely to be streams. Once those features are identified, we also combine that with a filtering process. So the features that we are going to map are the ones that are inside valleys or clearly connected to valleys by a contiguous channel-like feature. And so those two filters are used to decide which features we try to connect. Once we connect those features, then that process is a function of routing down, or it's actually upstream, using something called a priority flooding algorithm, which is a form of flow routing.
Awesome. So our next question is from Deborah Sward. With the high-resolution hydrography dataset, were there any areas that were particularly difficult to map due to LiDAR quality levels or the presence of significant tidal wetland?
Yes, there were many areas that were difficult to map. I would say that some of the primary challenges in this mapping process was that when we started, we did not realize that we were going to be mapping tidal wetlands or channel connections across tidal wetlands or open tidal waters and embayments. And so tidal areas in general were really complicated and difficult because most of our conceptual model for the automation was based on headwater channels. So that required some additional modification to our process that we didn't anticipate at the beginning. LiDAR quality wasn't a huge concern in most places, I would say. I think that it certainly does work better when the quality of the LiDAR was improved. And during the course of our mapping, we did have updates to the LiDAR that improved our data products, and that was nice to see. But I wouldn't call that a significant challenge, because I think when we started, most of the LiDAR in the Chesapeake Bay watershed was what I would call reasonable quality, that is qual 2. And in some cases it got better. I think the biggest challenge was in some cases we didn't have the data at all, but it was produced by the end of our project. I would say that the places that were the biggest challenge is when there's very little information in the terrain about where the stream flows. So urban areas, places where there's been massive amounts of human alteration of terrain that have nothing to do with the way the water flows, those types of landscapes are, in cities in general, are often challenges. To the extent that storm sewers follow terrain, then we do okay. But when there's a departure from that, it's much more challenging.
Great, thank you, Matt. So the next question is, how do you differentiate or classify road ditches, agricultural ditches, and other channels in your model?
Again, that's a machine learning approach. So we have features with lots of attributes that we've quantified, and that provides a very useful training data set. We can manually delineate some good examples of that, and David did spend quite a bit of time in the Delmarva Peninsula and other parts of the Chesapeake Bay watershed, different regions, developing training data. And then we use that to develop a machine learning approach that then classifies the features for us. I can tell you that some of the important features or attributes were how long and straight and uniform the dimensions of the feature were, and then whether it happened to occur in a large agricultural field versus along a road. Those were important attributes that we were able to develop. So things like that helped us immensely in developing the classification. I should say that the accuracy to those classifications were in excess of 95% in our training data, in our test data, I should say.
All right, so a follow-up to that, and you all can tell me if this has already been answered, but Lingdu asks, really interested in the methods for improving ditch connectivity. Is there a final product for a connected network? Because coastal areas are super flat, it is hard to define flow direction even from high resolution LiDAR. And great presentation.
Thank you. That was very kind of you. I completely agree that those are very challenging things to determine from terrain data. Unfortunately, those objectives were not part of our mapping objectives. We did not attempt to assess connectivity of all ditches, especially if the ditch went underground before it joined the stream network, nor did we really try to determine flow direction in the Delmarva Peninsula or other ditch networks explicitly, only trying to determine maybe the downslope connection for some of them if they were part of our stream network. So I don't think we really solved the problem that you're describing at all. And I know that there are many ditches in the Delmarva Peninsula that flow in different directions depending on the day and the hydrologic conditions. So we didn't even attempt to go down that road. And I sympathize with you if you were trying.
All right, next question. Is there any attribute in hydrography dataset so that we can do the aggregation for all upstream flow lines of a flow line? For instance, to see the effect of all upstream ag land use. And I could unmute this person if you need more elaboration.
I think I know this person and what they're asking about, and that's fine. We haven't effectively built that process into the data set, although those features are topologically connected, so they can be selected in that sense, but I'm not sure that they were. I guess the question is, have we built a network database from the data set? And I think the answer to that is no, we have not built it, but we've provided the information from which you could build it if you wanted to in a GIS. The thing that we have also not done is delineated the watersheds for these features. So if you wanted to aggregate land use up and down the network, you would have to do that still. That may be a future product that we produce for this data set.
Thank you so much, Matt. Thank you so much for your great presentation. My last question would be, could you please guide me what kind of attributes I can use in GIS to connect all the upstream flow lines of a flow line? Thank you.
I would be happy to have that conversation with you offline. I think that that is a great question, but I'm not sure that's a focus of everyone here. And it's probably a more complex process than I want to deliver verbally in a Q&A. But let's talk about that later.
Yeah, we've captured everybody's emails from when you signed up, so we'll be able to get in touch with you all that way. All right, the next question from Amy Fry is, will the newly released land use, land cover, and hydrography layer be available as an image service layer for easy use of the portal in ArcGIS Pro?
I will take that question. So I can share my screen here, but if you're in the app, any of these layers, you can hit the 3 dots and then go to details, and it will open the service link. So that should work for the hydro data, which has a tile layer and then a streamline layer, as well as the different land use, land cover layers. So you should be able to add those fairly easily to whatever project you need to add them to without having to download the whole thing.
All right, great. Thank you, Alicia. So the next question is from Kevin. Are HUC level profiles available or producible easily?
Is that the HUCs, are the HUC levels and their profiles available? Is that the question?
Let me see if I can unmute this participant. Kevin, you should be able to talk if you'd like to elaborate on your question.
Yes. If a user specified a HUC level, is it possible to get directly a profile for a specific HUC at a certain level, or can one produce those in the absence of GIS software?
So when you say a profile, do you mean like summary?
Yeah,
characterization of a HUC?
summary information of the land cover, land use, or change of either.
That's probably a question for Sarah, but we have not produced that kind of summary at the HUC level. That we're providing the data, trying not to anticipate what people want to do with it. But maybe
Sure.
Sarah can answer that for the land use and cover.
Yeah, there's not something out of the box absent of GIS software that can produce this. These are things that my team at the Bay Program produces a lot of these summaries, but there's not currently something out of the box that you can download at that scale.
Thank you.
All right, follow-up question from Amy Fry. If this data is to be published out, can it be marked as authoritative? So many other entities publish the data to meet their needs on AGOL, and it is not always easy to find the correct layer. And again, I could bring Amy off.
Yeah, I don't think it's currently marked that way, but we can make sure we get it there.
Yeah, thanks, Licia. And I think through Bay Program channels, we can do the same thing and kind of scrape the Conservancy's work and make it accessible through our Chesapeake data portal as well.
Amy, does that answer your question? All right, well, let us know in the chat. All right, the next question is from James Martin. Do the viewers include any ability for users to report misclassifications or discrepancies? Do you have any other process for reporting such discrepancies to help improve for future efforts?
There isn't anything in the app right now to enable that, but it's a good suggestion, so we'll think on it and look into it.
I agree, it's a great suggestion, and we would value that input.
Awesome. Great question, James. The next question is from Robert. Given the hydro mapping challenges in urban environments with extensive storm drains, is there an opportunity to incorporate municipal, county, storm drain GIS data to improve the accuracy?
Well, yes, except that it's not available everywhere and it's very inconsistent in terms of its accuracy in many locations. So for us, we opted to not try to collate and combine all that data because it was often unclear to us how accurate it would be, how up to date it is. And often those data sets are not topologically connected. So it's possible to do that. We certainly could incorporate it into our algorithm if such data sets exist, because it would be like providing more information to the classifier and to connect features. So that would not be at all unwelcome, but we did not do it in this case.
Great, thank you, Matt. So the next question is from Tim Wheeler. Did you map non-tidal wetlands?
Yes. So we mapped tidal wetlands, riverine wetlands, which are mostly floodplain wetlands, and then terrene wetlands as well.
Awesome. So this question might have already been answered, but how were hyper-resolution connectivity lines, culverts, connected/created?
Well, anytime we had to leave a mapped feature, which are the features that are released in the stream polygon layer, to connect two polygons, we call that a connector. And then we used the information in the high resolution land cover to determine what was in between two features. If it was open water, then we called it open water. If it was a road or some other kind of pavement, then we would classify it as going under pavement or road. And if it was vegetation of some kind or some indiscriminate value like barren, we might say it was just going under the land. So we use the land cover to interpret the type of connector that was being traversed or created. So anytime we passed outside of the features to connect two different features, that's how we determined it was a connector.
Awesome. Well, I'm not seeing any more questions in the chat. So Matt, Sarah, Alicia, thank you so much for a great presentation, and thank you to all the attendees for asking such terrific questions. So thank you all. We will have a follow-up email to the attendees with some just some follow-up information and the presentation itself, and answering any other questions we didn't get to elaborate on. So thanks everybody. That concludes our presentation, and enjoy the rest of your week.